Yeah, that works. Okay, so this is joint work with Ellis Kesterton. Right, so I'm going to be talking about programming with unboxed data. And by unboxed data, what I mean is basically without any forced heap indirections. And this is the standard in languages such as C or C++ or Rust. And there are a lot of reasons why we would want to have unboxed data as a default. So we're able to construct things like contiguous arrays, which give us constant time indexing into, large chunks of data. We can have unboxed integers, and generally we can pack very small data into like small space. We can represent protocol buffers or other, say, like network protocols and other packet formats. And generally, we can, be more precise about how we arrange data in memory, maybe to fit our access patterns and, to improve cache locality of access, things like that. Okay, so what's the problem? Well, the problem is that with dependent types, it is not so easy to have unboxed data. And the reason for that is that we cannot necessarily resolve the size that each type takes up in bytes at compile time. So this is a simple example of this, where we have a dependent function, and the return type of this function depends on the input. So if b is true, then it will be an integer. Otherwise, it will be a pair of integers. And the memory layout of an integer is different from a pair of integers. So it's not clear how we would compile this function without knowing what b is. And b will only really be known at runtime. And you could say, okay, maybe we can just take the maximum of both branches or something. But in general, we'll be able to have any function there that computes a type, and we will not really be able to know all the possible things it can be. And for this reason, pretty much every dependently typed language, and also most functional languages for some other reasons, will box pretty much everything. Okay. But what if we could actually have unboxed data in dependently typed languages? So the paper on stage compilation with two-level type theory by Andrzej Kovacs has this section in sort of the applications that say that perhaps you could have an object theory in a two-level type theory, which is actually where the types are indexed by memory representations. And this way we can actually, after staging, we resolve all the memory representations to concrete values, and therefore we might be able to compile this in a better way without having to box everything. So basically, we're just trying to see how far we can take this idea and what we can actually do with it. So I'm going to go through some goals. So the main goal is to have a language with dependent types where stack allocated unboxed data is the default. And we should also have an explicit boxing primitive for when we actually do want to use the heap. We should be able to have efficient and safe indexing into data. Because we have dependent types, we should be able to have the same kind of safe indexing. Since we have a concept of memory layouts, naturally we'll get a concept of zero size types, and it would be nice if this could correspond with computational irrelevance. And generally we would like to keep the primitives low. We don't want to just postulate that we have all this unboxed data that we can construct, but rather we should be able to build it up from like a small set of primitives, essentially. So yeah, the example would be that it would be nice if arrays are just iterated sigma types. And yeah, this has to be compatible with two-level type theory for general metaprogramming, but also for actually abstracting over these memory representations. Okay, so those are the goals, and there are some non-goals. So we're not really going to tackle manual memory management. So we're going to assume that we have some garbage collection scheme, because otherwise that would require us to have some kind of notion of resources, and that gets more complicated. And similarly, we're not going to be worrying about holding references to stack values, because that will have to involve things like lifetime analysis, and maybe it'll involve things like uniqueness or linearity, for example, in languages like Rust. And we're also not going to worry about unboxed closures just yet, because that also has to do with sort of figuring out what variables are captured. Okay, I'll talk a bit more about that later. Okay, so just for some setup and notation. So we have a two-level type theory. So the object level is what I will mostly focus on, and I'll use like Chi and term for the object level, and then for the meta level, it's Ty1 and term 1. And yeah, so the meta level is just going to be standard dependent type theory. This is some of the notation I'm using. So this is just the universe of types in the actual meta theory. And then we have type in the meta fragment of the language. And then I'll use this notation for sigma and pi types. And basically, I'm not going to really have many staging annotations. They're meant to be kind of inferable from the context, essentially. So depending on, in this case, depending on what A or B is, we can figure out what the whole thing should be. Okay. All right, so what does type system actually look like? So first we have this type on the meta level, which describes arrangements in memory, so memory layouts, essentially. So we have a few constants that come with this. So these are the basic layouts that you would have. So either a zero-sized layout, or just for single byte, or something that's pointer-sized, or something that's index-sized, which is basically an offset into memory. And also we can add up layouts together, which essentially means we're going to put the data one after the other. So for example, if we have pointer plus index plus 1, that's just a layout that describes a pointer followed by 2 integers followed by a single byte. Okay. Then once we have this, we can index the object level types by this layout. So instead of types just being set, it would be types are family over layouts. And then terms are, as usual, family over types. And in the object level language, we also have dependent types. And we will have a Grothendieck style universe. So we'll have this essentially a type of types indexed by layouts, and that's always going to be a zero-sized type. Okay. All right, so now we're going to go through the standard type formers and see how we can augment them with layout information. So to start with, functions are just going to be pointer sized. So they're just going to be a pointer to some allocation that contains like the code and also a pointer to the code and also maybe any captures that the function has. So if we have A is a type for layout small a and B is family of types for layout small b, then the function from A to B is going to be a pointer sized type. And here, crucially, the small b cannot really depend on the input of the function, right? So this is a dependent function, but it has to be uniform with respect to the memory layouts. Okay, so, right, and we can do a similar thing for pairs. So the pair of A and B is going to be a type whose size is going to be essentially like contiguously storing the data for A and the data for B. And similarly, we're not allowed for B to depend on this term here. And then we also have the unit type, which can actually exist for all layouts, and therefore it kind of acts like padding. So we can make it as big as we want, and we're never going to, yes.
At the beginning, you had an example for larger limitation for the size dependent on the output. So you cannot do this with the function of unit.
Yeah, I'm not worried. I mean, I have type in type everywhere, so I'm not really we can maybe talk about it after. Okay. Right, yeah. So the unit type acts like padding basically. Okay, so an example of this, so we can already make something kind of interesting. Here we're encoding an algebraic data type, in this case, the maybe type, but this is actually just going to be a tagged union at runtime. So we can define maybe of t is just going to be a sigma type. So, and the first projection is just going to be a tag that tells us if there's actually anything in there. And then if the tag is true, then the second projection will just contain the actual type t, or like an inhabitant of t. Otherwise, we're just going to pad it with whatever amount of appropriate space. And so overall, this will take up 1 plus b bytes. And we can also define the constructors of maybe like so, and we can also define the eliminator in the way you'd expect. Okay. Right, so continuing, now let's add some new type formers that don't usually exist. So first we'd have explicit boxing, which says if we have a type of any layout, we can just box it, and then we now have a type that's pointer sized. And we can go back and forth between box A and A. So there's that. So this is how we would be able to use a box. So if we have, say, like a sequence of 100 bytes, this is going to be a type of size 100, but if we box it, then it's going to be a box of this, which is going to be just type pointer. Okay. Okay, so we can do some stuff with this, but we can't do too much because actually a lot of the time we work with data whose size is only known at runtime. And maybe the most usual example of this is dynamic arrays, where we have, an array of size n contiguously stored, where n might be, I don't know, like a user input or something we don't know at compile time. So in order to handle this, we can introduce this sort of super type of layouts, which is going to be runtime size layouts. And every statically known layout is going to be also a runtime size layout, but there are also other kinds of runtime size layouts. And most usefully, there will be, if we have a layout, we can multiply it by some number, and that number might be known either at runtime or compile time. So it's going to be partially static, and that's going to give us a new layout. And then we can have codes of types for this new layout. And however, the actual, like when we have a term, its type should be of a statically known layout, so we can actually allocate it on the stack. Okay, then, so in order to actually construct inhabitants of types whose size is only known at runtime, we need a way to do that. And the way to do that is by this new type former that essentially represents the generation of runtime size data. So it takes any type of any layout. It might be only known at runtime, and it's just pointer sized. And for size types, it's pretty much equivalent to, make A is equivalent to A. And the way you can think of this is make A is basically a function that takes a mutable reference to some location and essentially fills it in with the data of A. Of course, we can't actually write this in the language, but this is sort of how it's going to be compiled. Okay. So then we can generalize pairs and units to this setting with make. So we can create pairs and units whose size is only known at runtime. And we can recover the previous versions as a special case because runtime compile time layouts are kind of a subtype of runtime layouts. Okay, so with all of this, we can actually define arrays. So we can define arrays as iterated pairs just by pattern matching on the size. So a zero-sized array is just a unit. And an array with n+1 elements is just going to be a sigma type, where the first projection will give us the element, and then for the rest we'll have the rest of the array. And so we can see that because we have the appropriate computation rules for this multiplication on layouts, the types and the sizes actually all match. So in this case, successor of n times t is going to be computed to t plus n times t, which is exactly the layout for dependent pairs. And using make, we can write functions that will generate runtime size data. For example, replicate. You can give it a natural number, which might only be known at runtime, and it will make an array of that size. Okay, so to actually use runtime size data, we will need to box them eventually. So in this case, we can define vectors and lists, which are kind of the usual types we have. But now we can do it in terms of arrays. So a vector is just going to be a boxed array. And then a list is just a pair of some length and then a vector of that length. But if we actually know the layout at compile time, then we can just directly operate on inhabitants of this type, right? So if we write something like this, we can type it as an array of 3 words, where word is just machine word type or whatever you want. And this is going to have this layout, which is statically known, and therefore we don't really need to box it. Okay, so we can basically reuse this across both levels. Okay, some other things. So since we have this notion of splitting up the universe of types based on layouts, and we have sort of the zero layout, then we can potentially introduce this concept of computational irrelevance just by having this type constructor that essentially acts like a modality that says for any type, in fact, it should be a question mark here. Yeah, for any type of any layout, which might only be known at runtime, we can consider that as a zero-size type. And this is, it basically has like a monadic interface where if you have an inhabitant of something, you can sort of erase it or forget that you have it. And if you have doubly erased something, it's just the same as having that thing erased. And the point of this is that we can eliminate any irrelevant thing into a zero-size type. So this eliminated looks something like this. And with some elaboration and syntax sugar, we can basically end up with a system that looks kind of similar to something like quantitative type theory. So for example, we can type this function at that gets an index, gets the element at a given index in a vector, and we don't really need to remember what the length index actually is. In a similar way that you write this in like Idris or Agda, for example. Okay. Yes, and then this is, I think, the last custom type former. So one thing with unboxed data is that when we want to project data out, in the case where we're boxing everything, like in the usual case with functional languages, we can just have projections, and these are not going to cost too much because each intermediate bit of data is going to be very small. But in this case, if we have like a huge array, for example, we don't want to keep having to project almost like all of it out until we get to the element we want. Instead, what we really want is to be able to build up like indexes into our contiguous data. And then once we build up the index we want, then we can actually go and access the element there. So to do this, we will basically introduce sort of like a pi type, but not really. So this, for any type A and B, which might only be known at runtime, we can form this type an index into A, giving us a B, essentially. And this is just index size, so it's just going to be compiled as an integer offset at runtime. And so the way we use this is when the subject is actually sized, then we get this sort of application-like operation. So if we have some subject A and then an index from A giving us B, then we can sort of make a B. And in the case where B is sized, then this also will give us the actual B itself. But we don't actually have an inverse of this operation like usual. So we don't have lambda abstractions to this type, but we do have composition, or like dependent composition, which says if we have an index from A to B and then an index from B to C, then we can get an index from A to C. So this is interpreted basically as just adding integers at runtime. So for example, the projections for the runtime size dependent pair would come with this indexing type, right? So if we have a dependent pair like this, then we can project out the first thing, and that's just an integer offset. In fact, it's just 0. And then we can also project out the second thing, and that's also an integer offset. And yeah, this can be dependent. And so, for example, we can compute array indices. So we can write this function like we would usually write. But now instead of saying fin_n to array tn to t, we have this indexing type at the end. And so we're basically saying we're just going to produce an inhabitant of this indexing type, and then we'll be able to use this application operator to actually get the element out of it in the end. So yeah, we would look something like this. So if we have a tape of 100 symbols, then we can index into it to get the 54th element, for example. Or if we have, say, some data structure that involves a game, and then we have an index into a game to give us the list of players in the game, then we can index into the game to access the players and specifically the third player, right? And when we are compiling this, we're not going to first project out the whole list of players and then project out the third player. We're first going to compute this whole index, and then we're going to straight away just compute the correct memory location and dereference it. Okay, so this is sort of the overview of all of the new type formers that we have on top of the basic ones of type theory. So yeah, we can make runtime size data with this. We can box any data to get it to be pointer sized. We have the irrelevance modality, and we can also index into data. Okay, so just some notes about how this is compiled. So yeah, layout will get translated to a fully static representation after staging. because it doesn't contain any object level data. So from that, we can just compute a byte size at compile time and know how much stack space to allocate for everything. And then this runtime size layout still contains object level terms after staging. So we cannot know its size at compile time, but we can know it at runtime. So we can essentially emit code that computes the correct size and then performs the correct allocations. Okay, so I haven't talked about memory management, but basically we can just implement reference counting with the system because the layouts tell us where all the pointers are. But alternatively, we could also use plug-and-play garbage collection, such as the POMGC or whatever other way you want to manage memory. Yeah, so for our implementation, we're just thinking of using reference counting, basically. And then mutation of data, which is also kind of important when you have unboxed data. I haven't talked really a lot about it, but generally it can be handled in a similar way to usually in functional languages, so with a SD monad or something similar to that. But maybe a better solution might involve having substructural features like linearity or uniqueness. But yeah, just some current progress. So we have a shallow embedding of the system in Agda. And we also have an untyped model that will essentially erase away all irrelevant data. So it justifies this irrelevance modality. And then there's an implementation of the system that is currently work in progress, but it's very close to being done. So hopefully soon we'll actually be able to use it. And yeah, we need to figure out what semantics we should have. And that's more like my question, if anyone has any idea of how we should actually justify all of these layouts and show some kind of correctness. And yeah, there's some future work. How much time is there left? Okay, then I'll leave this up. Thank you.